I just started recording. So basically, we have next week will be actually our last meeting, right? The seminar, I think, is supposed to run for 10 minutes. So we sort of need to start wrapping this up so that I can at least tell you a little bit about the ideas, how the conjecture is proven in dimension 3. It has been somewhat, I mean, if you think about all the topics we have discussed, I suppose it has had like a lot of variations. Just to add to that, we'll talk a little bit today about thermodynamics for some reasons that will become clear soon. So, thanks. I don't know if you remember that we discussed last time a little bit about vector fields, right? Where a vector field for us was just this idea, which can be made more precise, of like at each point in space, you draw an arrow, right? And for us, these arrows could be thought of, well, imagine that you're on a river, right? And you place like a tiny paper boat on the river. And so these arrows would tell you the direction in which the boat would like to move if you place it at a particular point, right? So maybe if you place the boat here and it doesn't get stuck in a canal like the one at Suez Canal, then like oh sorry, oh my god, like, you should have told me. I haven't shared my iPad, right? Can everyone see it now? Good. So basically what I was saying is like, right, like you draw a bunch of arrows, think of them as the velocity, giving you like the velocity that a boat of paper would have if you place a boat at a particular point on the river. Okay, so for example here, if you had placed a boat on this point, it seems that this is like the trajectory that the boat would have wanted to take, right? So here, like you have so this would be like the a specific trajectory the boat could take. Right? Is that making sense? Notice that this particular trajectory is just like some type of curve, right? Which is just some curve. Is that okay? And so in general, but placing the boat at different places on the river, like it may just follow different. You may like you start getting different curves, right, on the river, which are just the trajectory that the boat would take depending or on where it was placed. Is that making sense? And again, maybe not everyone has taken uh, calculus before, but uh, you have this curve and you have certain arrows or things that are sort of tangent to the curve, right? So the arrows are tangent to the curve in some way. Okay. And again, if you have taken calculus, you know that things related to tangents, to, to tangent curves or tangency has to do with something that's called the derivative, right? So this is related to derivatives. In fact, what's going on is that sort of the arrow, uh, if you want, like, again, like for those who have seen this, and if you haven't, don't worry about it. But essentially the arrow is um, like, it's sort of like the derivative of the position of the boat, the rate of change of the position of the boat. Okay. So there are like, in mathematics, there are these problems, like the way in which you think about this in mathematics is that you had like a boat or like some object, and you just want to see how that object behaves in time by specifying its velocity, right? So like, so here, like the idea, the goal is to understand how the boat has to move in time if we know what the velocity should be. Is that making sense? So like I'm telling you, okay, like I know that at this position, the velocity has to be like 50 miles per hour. I mean, strictly speaking, velocity also involves like a direction. So let's say pointing northeast. And you know that in this other position, the velocity had to be 75 miles per hour, pointing south, and so on. And if I tell you what the velocity is supposed to be at every instant in time, can you tell me how the actual trajectory of the curve or of the boat or the person who's supposed to move under those conditions, right? So basically, what you're trying to do is like sort of find the curve if you know what the velocities are what like the tangent vectors of the curve have to be. Uh, this is what's called solving a differential equation for those who have seen this. So this is called solving a differential equation. Is that making sense? So in a sense, like solving a differential equation is like finding a particular function or equation if you know something about how that uh, function is supposed to change. Okay, so here is like, what this means is finding a particular, finding how a function is supposed to be, function or equation is supposed to look like So a very silly example would be that it, like, for example, like say they told you, oh, here's your here's a bank account, right? You know that at the beginning of the year, you had $100, and I will tell you each day how much money you're going to be adding or subtracting to this bank account. So you're going to be given like a rate of change. You're going to be given like a ratio of how much money per day you're being given, or how much money per day is being inserted or taken away from your bank account, right? And from that, you should tell me what is the exact amount of money that you have on your bank account at each day. Is that making sense? Or in biology, this is used a lot because maybe they tell you, well, you like, like I think biologists liked, for many reasons, rabbit examples. So you have like a population of rabbits, and like, you started with 10 members in the population or 100 members, and there are some rules that tell you how fast the members are reproducing or dying, right? These are called like sometimes logistic growth equations or things like that. And from knowing how fast, right, like a ratio or like a rate of change, how fast the population is supposed to grow, you can tell what the actual size is. This is similar, I suppose, now with the COVID models, right? Like the idea is that you have some model of how the disease is supposed, how quickly like say a rate at which the disease is supposed to spread. And from there, you have to predict the actual number of infected people or deaths at every day, right? So you want to know a quantity from understanding, like from knowledge, given the knowledge of how fast that quantity is supposed to to change. Okay, so there's like just to show you a couple of animations about this. Why the beat? Oh yeah, yeah, yeah. I see what happened. Give me a second. Sorry. Uh, can everyone see this? The slope fields from demonstrations project. Okay, so essentially what's happening here, again, is that you're being given like some vector fields. If you ever take differential equations, which is Math 244, has anyone taken that class or plans on taking it? Well, if you ever take it, you remember this day. You basically can draw like a bunch of arrows on the XY plane, which are sort of like the ones that you see here. They're like they can be drawn according to different formulas, which are like the different options that I'm doing here by switching it. And again, each arrow is telling you like how fast the position, like each arrow is telling you how fast the position is changing, at how fast the position of the boat is changing at that moment, because it's trying to give you like some sort of velocity. And again, from physics, you know that velocity is like displacement over time, more or less. And so yeah, oh, this looks nice. And then depending on like of where you place the boat. Like imagine like this black dot that I have placed a boat here, like then the black dot will move along a trajectory specified by these lines. Okay. And depending on the particular, on the particular rule that I had chosen, the motion that you end up getting looks different. Okay, but like the point here is that mathematically what's going on is that you're specifying how fast the dot is supposed to move. That's what you know, and from knowing that, you can sort of tell me or predict the position at every point. Is that making sense? So there, like you're given like a rule for the rate of change, basically. So why is this interesting or useful? I mean, I suppose everything will be cleared up next week during our last meeting. But essentially what's going on is, let me give you another analogy of what's happening. Let's go back to. Everyone has heard about thermodynamics. How about entropy? How about the second law of thermodynamics? I suppose if you have heard entropy, you have heard about the second law. But there's like this principle, right, about like, back in the day, like thermodynamics is like the theory about like, used or developed during the beginning of the Industrial Revolution for how heat engines are supposed to work, how heat is transferred between different bodies. In particular, actually, at the beginning, they had like a theory, which I don't know if you have heard. It was called the theory of the caloric. Where somehow, like, bodies, like the reason why there was like heat transfer between bodies was because there was some sort of substance called the caloric that was like literally transferred from one body to the other, and that has sort of remained in our current like language when you talk about calories. Like actually, that's where calories come from. Like the concept of calories, it's like a remnant from this caloric theory. Uh, but then like heat was later understood like in terms of like temperature difference, like temperature differences and energy, and so it's no longer regarded as some sort of substance. But in any case, like the point is that there's this thing. I mean, let's think about this for a second, right? Let's say that you're inside a room, and at the beginning, like maybe your room is starting to get cold, right? I suppose we still haven't left the winter altogether. There's still a few more days with cold days, right? And so you have some fireplace. I mean, you want to turn on the heat, or you have a heater, and right at first, you know what happens if you think about the temperature, right? Is that it will start. If you thought about this fireplace as providing like a constant source of heat, right? Then what happens is that like the temperature obviously will start getting warmer, or will start increasing close to the fireplace, right? But then you know, as time goes by, more and more parts of the room start increasing in temperature, right? And eventually, if you wait sufficiently long amount of time, uh, the sort of like the temperature stabilizes, and more or less it reaches like the temperature like of the fire, at which the fire, well, like the temperature like at which you turn on the AC or the heater, right? Like I suppose with a heater it's a better example, because you can just like choose to put it like at 70 degrees Fahrenheit, right? So if you wait enough time, right, and you will see like all the temperature unit like reach like a uniform value of 70 degrees, right? So imagine you turn on the heater. And at first, like the different parts of the room have different temperatures. But as time goes by, right, uh, the sort of the room reaches like the temperature of the room reaches a constant value or a uniform value. Well, I guess in this example, say of 70 degrees. Let's say. Is that making sense, right? Like, I mean, I suppose this matches everyone's experience of how uh, heat propagates, right? Or how temperatures propagate on a room when you turn the AC on or the heater on, right? And so the point is that here, like as time goes by, things become more homogeneous. That's like what I'm trying to say, right? Is that making sense? Because again, like maybe you went from a state where only very close to the heater you had 70 degrees Fahrenheit, and other places of the room had like a different distribution of temperature. And as you wait more and more, then more places, like the temperature of the room all starts behaving the same way. Is that okay? Good. Now, why is this? In fact, there's an equation called the heat equation, which is an equation that tells you how the temperature, like it's an equation that tells you how the temperature is supposed to change over time. So this is similar to the problem that we had discussed before, because before, essentially, I was giving you like a rule that told you how the boat was supposed to move, right? So I was giving you a rule for the velocities of the boat, and here I'm giving you a rule for how the temperature is supposed to change. So I'm giving you like a rule for the rate of change of temperature, right? So like the basics are that you're given a rule for the rate of change of temperature, and from there you have to find the actual pattern of the temperature profile. So you have what the actual formula for the temperature is, if you want to say it in some more unprecise sense. So essentially, you're given an evolution, a rule for how the temperature evolves, and from there you figure out the expression for the temperature. Okay. So the heat equation is like one of these famous equations, and there's a, let me put it here. I think I got it. Yeah, let's try to, let me show you. Like this is sort of like the typical thing that you will look at if you ever take like an engineering class. Everyone sees this graph. Yeah. So the idea of the heat equation is that it gives you like a profile. I mean, at the end, it gives you like typical examples here are like for example, you have like a rod, like a bar of metal, and you heat like the ends of the rod, or you do something like where you know the values of the rod at the end, and then you're trying to figure out how the temperature at any point along this rod is supposed to be, what the values is supposed to be. And again, like we don't care too much about the specifics of how that works, but only that if you see this graph, if you look at this graph, this axis represents time. So meaning that as you move along these values of 0, 0 0.5, 1, 1.52, you're letting time run by the clock. So if you notice it, like the graph looks a little bit more different at the beginning at time 0, and near time 2 is already more and more uniform, right? And in fact, the point is that if you increase the conductivity of the rod, meaning how easily heat propagates along the rod, then that means that this phenomena takes less time to occur, because then everything can try to uniformize faster. And so do you see me? I'm here, like there's some something called conductivity parameter. And I don't know if you see that as you increase the parameter, the graph becomes more and more flat. Is that clear? And if you again decrease it, then it's harder for heat to transfer among different places along the rod, and so it would take more time for like everything to um, you mean like what does doing this increasing this is doing, or what do you mean by increasing terms? Oh, I think this is just that's a good point. This approximation like the thing is like what's happening, right? What's happening is like usually the way in which these problems are solved. Right. Good. That's what I was going to say. Like strictly speaking, like the way to solve these problems is with something called Fourier Series, which engineers like a lot, which is like a version of like similar to Taylor series. But if you have, it doesn't matter if you haven't seen that. The idea is like strictly speaking, the actual solution, the way in which you write them has like infinitely many terms, which is obviously on a computer you could not represent that. So you sort of have to include just some like some number of terms, and so this is telling you how many terms you're including in that representation. So meaning that as you include more terms, like the solution is more like the graph is more an accurate version of what's going on. But yeah, that's basically what's happening with what they mean by terms here. Even solving these equations is not an easy business. So yeah. But it's just saying like so what I'm trying to say is like the computer is not being fed the actual solution. It's just being fed like an approximate solution, and increasing the number of terms is telling you is adding more and more of these terms of this approximation to the computer, to the program. So it's like a more accurate picture. So like but the terms like really does not matter too much for us. What's more important is the qualitative nature, where if you like again increase the conductivity, then everything flattens out more easily. And if you decrease the conductivity, everything takes more and more time to flatten out, because there's less like transmission of heat, right? So that's basically the basics of the heat equation. But what you're seeing here is like a phenomena where like things are trying to become more and more uniform. Okay, that's basically what I'm trying to get at. So by the way, there's another funny one here. Let's see if I can show it to you as well. Right, you can sort of play around with this heat equation in many ways. So here's like a representation of a solution for a couple in bed with a cat. And this tells you how the heat is supposed to transfer uh, in this situation. So yeah, like you can sort of see like the details of the equation and how the solution is supposed to behave and other things. Okay, but the point is that there's like a tendency for making things more uniform, right? So like the takeaway here, let me go back to the so like the important lesson here is that you can in the heat equation in the temperature problem, or as time goes by, uh, the the temperature distribution becomes more and more homogeneous. Okay. So there, like, the reason why I'm mentioning this is that, like, basically what happens is that there are like similar things that you can do to not like quantities like heat, but like to curves themselves, for example. So they're like there's similar uh, processes or like equations that you can study for geometric shapes. So like the idea is that you can do a similar, there's a similar story that can be done for studying geometric shapes, or more precisely for now, say curves on the xy plane. Okay, so I don't know if you remember I don't know if you remember when we talked about curves, right? We talked about the curvature of a curve. Uh, you remember this? And so like what you would draw to find the curvature of a curve is that you would draw like these circles, which are called oscillating circles, right? And then the curvature of a curve at a point is like just like 1 over the radius of this of the oscillating circle. Is that okay? Does this look familiar? Everyone remembers this? Here's like a more, now that we have talked a little bit about vectors, here's like a more a different way to think about what's happening here. or like what we want to uh, talk about right now is that if you have a curve, then you have vectors that you can draw, which are like sort of following the curve, right? So these are called tangent vectors or velocity vectors. But so they sort of follow the curve, or they give you the direction of the curve. Uh, there are other vectors which are called the normal vector, which again, unless as you might expect from the picture or from the word, well, actually, I suppose it's not clear from the word. Uh, by normal, I mean perpendicular vectors. Here, maybe. So the green vectors are perpendicular. I should draw them better. I killed my curve. And these are called normal vectors. Normal vectors, or and they are related to like the concavity of the curve, or the how the curve. If you thought about more physical terms, like they're also related to uh, the curvature or the acceleration of a particle that follows that curve. I mean, they sort of determine the bending of the curve. They're related to how the curve bends. But there's a thing that you could, is the picture at least clear? Like that if you have a curve, you have these red vectors, which are sort of parallel to the curve. And then you have these other perpendicular vectors, which are the green ones, right? And so what you can do, like one thing you could do with the curve is just to demand that, like, you can imagine like work starting with a given curve and ask for it to move, to try to move it in the direction determined by the normal vectors. So what you can do, and this is called the let's see, what's the precise term? Oh, if you want the technical term, so you can go to Wikipedia. Like you start with the curve and you start try to move, and you try to move it in the direction of the normal vectors. So by that I mean, for example, like imagine you take the circle. The circle is a nice example because in that case, like the velocity vectors look like this, or the tangent vectors look at it like this on the circle, and then the normal vectors like look at what you call like centripetal acceleration. If you know this concept from physics. Has everyone heard that like this centripetal acceleration thing? The point is that in this particular case, like what I'm trying to say is like if you thought of like the circle being as a precisely center at the origin on the xy plane, like literally these normal vectors point towards the origin, meaning they point towards the center. So if, like what I'm trying to say is like I'm telling you, like imagine you have this circle and now you're trying with your fingers to bend it or move it in the direction of the normal vector. So what do you think is going to happen with the circle? If you try to move the curve in the direction given, think of the curve as now as a type of boat, right? A circular boat. Now we're trying. Now the green vectors are sort of like this current, these flow lines, right? It's just like a circular boat made of clay, so it's allowed to shrink or expand. So what happens if you try to move the boat in the direction of the green vectors? It will get smaller, right? Is that clear to everyone? In fact, eventually what it's going to try to do is reach the size of a point, and when it reaches like a point, it reaches like what's called like a singularity. So this is like the future direction. So as you go into the future, the circle starts shrinking and shrinking more, and you get to the extreme case of a point, and this is called the singularity. This is not that different actually from how, if you have heard about the Big Bang, when they say that there's like a singularity of the Big Bang, this is not that similar from how it's somehow in a sense related to those type similar singularities that occur during cosmology with the equations. Uh, but here's the cool thing. Let me switch. Oops, wrong screen share. It should have been the Firefox one. Here it is. Can everyone see Firefox? So if you go to your course site, you'll see that I have posted a link here. Okay, can everyone see like the curve? Okay, so here's what's going on. This is a cool app where you just draw your favorite curve in the world, right? Let me draw one. And this curve is going to evolve in the same way as we just evolved the circle, meaning that, like, imagine you find some normal vectors. And then the curve is just going to follow the rule, like the motion determined by these normal vectors. Okay. Does everyone see what's going on? Oh, this is great. And so essentially what's happening, I just enjoy doing this so much. Let's just enjoy this for a second. Okay. This is almost similar to our, ooh, this disappeared very quickly. But you know, this was like sort of like our circle. And then you can draw like a hand. But like, I don't know if you like, what's the qualitative feature that you should take about from here? What's happening is that essentially you had a curve which was very irregular, right? Look at the curves that I'm drawing, right? And by using this flow, you're sort of homogenizing it, right? Does everyone see what, in what sense? Like, it's becoming more and more pretty. It's being it's like this analog of a surgeon for aesthetic surgeon for curves. Like, they're becoming more circular if you think of circles as a perfect shape, right? And after they sort of like reach this more circular form, they try, like, they follow the same fate as the circle, right? They just start collapsing, right? Great, great, exactly. This is what's good, good, good. Yes, yeah, exactly. This is sort of like the point of the analogy. So there's like a similar thing that you could do. The idea of Ricci flow. Like, just to start like telling you what's happening. Like, this was also what's going to be mentioned more like at last week. But so like what happens is, like, imagine that you had like a sphere, right? But you start heating it, right? So I mean, like a globe, and you start hitting it, and so it looks like all horrible now, right? Uh, there's like a similar type of rule that you can apply to this, like this irregular globe, that will start sort of correcting like the irregularities and like making it like more nice, right? Until it reaches again like its original spherical form, right? This type of rule that you up or to another surface, right? Like, you could take a donut that I had shown you, and imagine like you just start putting your, like, again, if this were like of a different material, you could imagine like some sort of clay or other thing. You could imagine just start like fingering it all over the place, and then like it has like a bunch of like horrible like saddles and mountains and peaks, right? But like you could, like, the idea is like you could imagine like applying some rule to it that sort of like starts making it more symmetric, right? Until it recovers its donut-like shape. Is that making sense? In the same way in which, I don't know if you remember, almost like at the first time of the course, when I told you when we were trying to study universes, really one-dimensional universes, there were not that many options. They were like essentially all sort of like equivalent to like a closed interval, right? Or to some sort of interval, or if you had this property where you could return by just walking in one direction, if you could return to where you started, they were like more or less like circles. And one way to realize this explicitly is that if you draw some other like weird shaped one-dimensional universe and you apply this sort of flow to it, this is called like a flow. If you apply this rule to it, it sort of tries to become more and more circular. Is this making sense? So like the point is that, right, on curves, if you apply this rule of following the normal vector, you start getting from a horrible, ugly curve, you start getting a more pretty curve, which becomes more and more as a circle. It reaches like a circle. Once it reaches a circle, it will try to collapse into a point, which is what you see always in this animation. With surfaces, you can do something similar. You could have, like, the idea with surfaces is that you, again, like, start with a random surface, and essentially when you apply this flow to it, or like an analog of this flow or of this rule, you get like one of the model surfaces that we had drawn one day when we did like the taxonomy, like the pure circle, sorry, the pure sphere, the donut with one hole, or the donut with two holes or three holes. Like all the like any surface would sort of become one of those in the end, as you apply like a similar rule to deform it. And for the three universes, for the three manifold, the idea of the Ricci flow is somewhat similar, that you start with a arbitrary three-dimensional universe, and you sort of apply like an generalization of this idea, which is determined by something called the Ricci curvature. And the three-dimensional universe wants to sort of become more and more symmetric. Okay, it's just that in the three-dimensional case, there are like a couple more things that can happen, because even here you saw that things want to become singularities, in the sense that they may want to collapse to a point. And the three-dimensional case, like there's similar things that happen. So as you let time go by, you have to you have to do certain things to start preventing like the universe to just collapse to a point and you lose all the information. So like what I'm saying is, like, you sort of have to right before it became a point, you sort of pause it, do something to it, so that you can keep running this program down without like reaching like a point or something bad, because once you reach a point, like all the information is sort of lost. And so but yeah, like the idea is like there's like a similar process going on that you can apply to the universe of like these three-dimensional universes, where they try to become more and more homogeneous, basically. In fact, by the way, like this animation is even more cool because it says closed curve. Like, strictly speaking, the curves that I have drawn have not intersected themselves. Like, if for this big animation, you can even like self-intersect them. So you can do something like that. This is a little bit different from like our cases, but like you can also draw things like that. And let's see, there's another one which is very cool here. Which also shows you like it's again like this type of flow applied, or evolution rule applied to this curve. The cool thing about doing it is like they never, like, if the curve didn't intersect at the beginning, it never intersects itself. So it's sort of trying to unwrap, it's trying to become circular without crossing itself. So it is very nice how it ends up looking. Okay. So the point of these examples is for you to I have to screen share. So what I'm trying to say is that with these examples, if you start with a random curve, basically, like as you do apply this rule, or strictly speaking, it's called apply the flow. The curve tries to become a circle, and then from the circle, it will try to collapse, right? It will go into a circle, becomes more circular, and then it collapses, right? And like something similar is happening if you had started with like a random surface. So here's like a random curve. If you had started with a random surface, as you applied the rule, well, in this case, like the point is that the way I'm drawing it has like sort of three holes. The idea, this is a cool idea, that like the property of having three holes somehow is not going to be destroyed by the rule. And so what this one would try to become is like this more like beautiful, perfect pretzel that we had drawn in the past. But if you had tried to like sort of do like, if you think of this as a like a punch ball, right? This one has no holes, and so when you apply the rule, this just will try to become like a perfect sphere, meaning that in this case, like when you started with your random surface, uh, its fate is more or less determined by the number of holes that it had. So if you have like a random surface, is like what it's trying to become in the end. It's sort of determined by by the number of holes, like its end final form determined by the normal form determined by the number of holes. Like somehow, like the idea is like the number of holes can be you can tell how many holes a surface has regardless of how deformed it is presented to you. Well, I mean, there's like a difference between like having like a compelling idea, right, and making the details work out. So I think the biggest issue, like for example, again, I think I mentioned this like the first day. I don't myself like really have ever tried to read the proof. And if I wanted, I suppose it would take me a great number of months or more to really try to understand every single detail. Who knows how much, maybe 1 or 2 years, but or more. Like the people who tried to understand the proof at the beginning, like it took them a long time. The thing is like even you see already what's happening in the curve situation, where like things wanted to become a point. Again, this is sort of like the analog of in cosmology when people talk about singularities and other things like the Big Bang. In the case of three manifolds or three-dimensional universes, you have to understand all the ways in which the flow or this rule can go wrong. And then you have to sort of like see how ways to prevent that from happening and have a lot of control of how you are like keeping track of that. So it's just that there are like too many. There's another thing, like, I mean, mathematically, like there are other more basic things that you have to show that like for example in mathematics you will need to show like things that like that this has to limit something, in the sense that just because you say, oh, run this rule, yeah, just because you say, oh, let's apply this rule, that doesn't mean that the rule will give you like a final definite answer, if you know what I mean. There are just too many things going there. But I do agree that the idea is compelling. You see, like it's sort of explainable to someone with without many math classes, which is why we're doing this seminar for zero students. But it is just like devil is in the detail type situation, you know. So it's not like once you get into the nitty gritty, it's a lot more overwhelming. Right, and like just like a lot of like right, like understanding like a lot of the properties of this flow, like again like just like basic things about the flow and quantitative estimates, where what that's called, like how much time it would take for you reaching like the problematic solution or a singularity, and once before reaching the singularity, what can you do and other things. So yeah, it's just like a lot of technical things that go into that. Now, like the reason why I started talking about temperature is that if you think about this, like there's some analogy that I'm trying to draw, in the sense that temperature, right? With temperature, you can imagine like starting with a crazy situation where temperature is all spread out throughout the room, right? Like they're totally different temperatures at that corner and in this corner and this corner, right? But if you let time go by, and things move according to the heat equation, then things become more uniform, right? So there's something similar happening here. And in fact, the Ricci flow has many formal properties to how temperature evolves, in the sense that, again, you could have started with this crazy surface or crazy curve, but if you just let it evolve, right? If you let time go by, it just wants to become more and more homogeneous, right? So there's like a property in thermodynamical systems which always increases over time, which is called entropy, right? And the thing is, like on the Ricci flow side, there's an analogous quantity to entropy that you can define that also increases over time. And so I guess like for the last class, I'll tell you a little bit more about entropy because I think that's interesting. Just ways to think about entropy, and I'll say a little bit more about how this is all related to the Ricci flow. But at least it's useful to understand, like it's easier to understand the entropy from the thermodynamical side than there's like an analogous notion of entropy in these flow type equations, but there's more physical intuition for the thermodynamics. So I'll tell you a little bit about entropy in thermodynamics and also in information theory, like how you can even talk about the entropy of a message, like of an email. How much entropy an email, like how much entropy is stored in a piece of code or things like that. And so we'll talk a little bit about that, which is a little bit cool. But yeah, this is like the basic idea of how the proof of the Poincare conjecture goes is that you sort of try to run a flow or apply a rule that starts changing your universe into some more basic forms that you do understand better, like some more like homogeneous or symmetric forms of the universe, of the possible universes. So that's more or less how it goes. But I think this is a good place to end for today, because like with 10 more minutes, I cannot say that much more. But I think now, hopefully this gives you like a more clear, I think that curve animation helps a little bit to have a better perspective of what's going on. So I'll see you for our last class next Wednesday. Perfect. No, I think Ricci flow. I don't think. I think Paramount noticed that you could use Ricci flow to prove the Poincare conjecture, but I don't think Ricci himself had studied Ricci flow for this particular goal. Yeah. I think it was a natural thing to study for other reasons, but not. Yeah, I don't remember. It could be that he can mention, like maybe he can mention already some applications. I'm not quite certain about the history actually. But I think the book, if you are still reading the book, I think it may be mentioned somewhere. If you reach towards the later chapters. Good, good. I'll see you all then.